It's the intro video for BC Calculus, and we're going to be looking here at Chapter 9, kind of an intro, sequences and series. Okay, so we talked about this a little bit in AB, and this is going to just end up being kind of a helpful foundation set of thoughts as we turn our attention towards relative rates of growth. So I'm gonna present these as sort of a rankings of functions and how fast they grow. And so let's take a look at these right here. So first of all, the function that grows the fastest is x to the factorial, at least the ones we're going to be looking at. X factorial grows faster than any other function besides x to the x. We will not be looking at x to the x as a type of function in our course. And so for our purposes, x factorial is going to be the fastest growing. So if you wanted to, you could compare 10 to the x, which is an exponential, to x factorial. And you could use your calculator, you could use a table to figure this out, but x factorial will always grow faster than any exponential or really any other function besides x to the x. So it doesn't, depending on what the base is, like in this case I put 10 to the x, if it was maybe 100 to the x, it would certainly appear for a while that the 100 to the x is going to grow faster, but eventually x factorial will grow not just faster, but infinitely faster than 10 to the x. So the number one ranking, the fastest growing function is x factorial. So that's the top dog as far as rate of growth. Okay, then number two is exponentials. So an example of an exponential would be 10 to the x, 2 to the x, 5 to the x, things like that. And so we see down here, we could compare 2 to the x with x to the 10th. You'd find out that early on x to the 10th is higher than 2 to the x, but eventually you'll see that 2 to the x does eventually overtake x to the 10th and grow not just faster, again, but infinitely faster. Then number three ranking goes to polynomials. So polynomials, they don't grow as fast as exponentials, they don't grow as fast as factorials, but they do grow, they do have the next spot in the rankings. So we could compare x to the something. Now technically that's not a polynomial, but if the base is a variable and the exponent is a number, we're going to kind of put it in this class of functions. We could compare that with natural log of x. And certainly here, natural log of x for a while is going to seem like it grows faster, but again, eventually x to the 0.1 will grow faster, infinitely faster than natural log of x. And the last place, the slowest growing function would be the logarithms, like natural log of x. Logarithms. There we go. So those are the slowest growing functions. As x gets bigger and bigger, they grow the slowest. So that's your rankings right there. And again, we're not going to do a whole lot with this at the moment, but as we get a little bit further into Chapter 9, where I think we're going to see some places where your intuition about this is really going to serve you well. Okay, so a second ago I mentioned that this rate of growth, the relative rates of growth, are going to be judged as x gets bigger and bigger and bigger. And so we're talking about a limit here. So if we evaluate an expression like this will tell us which function is growing faster, f or g. So if we take that expression and we evaluate it and we get this, that means that f is growing faster than g. If we did this, we got 0, that means the same thing, means f is growing faster than g. So with these scenarios, you're either going to get infinity or 0, and that will tell you which one's growing faster. And f and g do grow at the same rate, the same relative rate, if you calculate that limit and you just get some number other than 0. That means that they're growing at the same rate. Okay, so I thought we'd do one of these real quick here. So let's take a look at our example. So I've chosen a relatively tricky example to look at here. There we go. So it says the limit as x approaches infinity of x plus 1 factorial over x factorial times 2 to the x. So at first glance, this one might look kind of interesting because you got a factorial on the top, you got a factorial on the denominator, and so you might be tempted to say these will grow at the same rate. What I'm about to show you is going to be something that will be super useful as we move forward into Chapter 9 a little bit later. But here's what we're going to do. I'm going to expand out what the factorial means. We're going to be able to simplify this quite a bit and make this a little bit easier. So x plus 1 factorial would be x plus 1 times x minus 1 times x minus 2, so on and so forth. X factorial would be x times x minus 1 times x minus 2, so on and so forth, and of course still times 2 to the x. So you probably can see this. The key to understanding how this works is to see that the x will cancel out with the x minus 1s would cancel, the x minus 2s would cancel, and the so on and so forth would also cancel, leaving us with a much simpler looking expression like this. And here's where your rankings would come into play. You would look at the numerator and you would say that that is a polynomial. And you look at the denominator and realize that that is an exponential. And if you know your rankings, you know that the exponential will eventually grow infinitely faster than the polynomial. Therefore, the value of this limit is 0. Okay, so I've skipped a little section in your notes there. We're going to be doing those in class. But I thought we'd talk a little bit about sequences here before we finish our video. So a sequence is simply a function whose domain is the set of non-negative integers. And there's always some kind of a pattern here. The pattern is defined by some relationship. The terminology here, we typically use this, A3, A sub 3, to represent the third term instead of A of 3, right? So it is a function, but we'll use a slightly different looking notation for this. An example you might have seen in the past lists the first 4 terms of the sequence defined by this, or maybe it asks for the 30th term in some sequence. Lots of different questions could be asked here. We're going to be focusing in our class here in this video on the limit of a sequence. This is going to be pretty important as we start to talk about series here in a little bit. So the limit of a sequence, let me get this here. There we go. We're going to be focusing on the pattern of the sequence's terms, and does that pattern seem to be approaching a limiting value? Does it seem to be kind of settling on or around a certain value? Terminology here, if the terms of the sequence don't appear to be reaching sort of a limiting value, then we would say that the sequence diverges. And if they do, if the terms do seem to be reaching a limiting value, we would say that the sequence converges. So 2 important words there that we will we'll use quite a bit in this chapter. So I think it's kind of nice to view these sorts of questions through the lens of a calculator. And so I think what we're going to do with these numbers down here, 1, 2, and 3, we're going to use the calculator to help us. So I think I'll try to split my screen and we'll see how this goes. Okay, so the first thing we're going to do here on our calculator is we're going to get into the right mode. So you can see here that I am in polar mode right now. So I'm going to put it into sequence mode, so over there on the right. So I hit enter, now I'm in sequence mode. So for number 1, what I'm going to do is enter that function over there for number 1. It says 3 plus -1 to the n. So if I'm in sequence mode, I'll get this kind of a screen. I can enter this in. So 3 plus -1 to the n. So I'm going to graph this now, and I think I'll just try to do a zoom 6, and we'll see how that goes. There we go. Maybe I'll I'll change my window a little bit, make my x min 0 and my x max maybe 20 or something like that. We'll be able to for sure see the pattern here. I guess I could, there we go, we'll put our n max out there at 20. We can see a little bit more of it. There we go. Okay, so the idea here would be looking for a pattern. So if we're looking for where this sequence converges, I'm looking for a limiting value. So in other words, each of these little dots represents a term in the sequence. Do we seem to be kind of narrowing down to any one number within this graph or not? So what I'm seeing here is that the terms in the sequence are simply just bouncing up and down, right? So it looks like 2, 4, 2, 4, 2, 4, 2, 4. And it doesn't look like the terms in the sequence are really heading towards any one particular number. The terms are just oscillating between 2 and 4. So as far as does this sequence converge or diverge, I would say that this sequence diverges simply because the terms do not appear to be converging towards any one number. The pattern within those terms is not heading towards a limiting value. We're just bouncing back and forth between 2 and 4. Okay, so let's take a look at another one. Let's take a look at number 2. Okay, so I've entered this into my calculator, kind of like we did before, and now I'm going to look at the same kind of graph. So I'll hit graph here, and this is obviously a very different looking graph. I'm going to change my y-axis scale here. So my window, I'm going to say my y's are going to go from like -1 to 1 maybe. You can tell it's pretty compressed vertically. So let's see what this looks like. Okay, looks like maybe I lost the top of something there. So let's see, maybe I go -1 to 2 on my y's. Okay, there we go. So this is, like I said, very different looking graph. You can see, of course, that the terms appear to increase through here, and then they start decreasing. But then you notice kind of like this asymptotic behavior, right? It's the terms seem to be approaching a limiting value. And I would say, based on the way this graph looks, that these terms are probably approaching a value of 0, appear to be getting closer and closer to the x-axis. So again, based on that reasoning from the graph, I would say that this sequence converges. Okay, let's take a look at our final one here, number 3. Okay, so again, you can see that I have entered that sequence into my function there. So I'm going to take a look at a graph of this now. Maybe I'll change the color. This one's kind of hard to see. Maybe that'll be better. Okay, so anyways, there's that. I think I'm going to change my window a little bit. I think I'll go with my y's -1 to 1. And there we go. So once again, you can kind of see this is a different looking sequence, very different than the last one, because I've got a negative term in my sequence, and then a positive, and then a negative, and then a positive, and then a negative, and then it gets really, really hard to see there as the terms get closer and closer to the x-axis. Later on, we're going to call this an alternating pattern, and simply called alternating because the terms alternate in sign, plus, minus, so on and so forth. So the question is, does this sequence appear to be converging or diverging? And I would say that this one appears to be converging, because as I look at the graph, it sure looks like those terms are getting closer and closer to 0 as x gets bigger and bigger, and so we would call this a converging sequence. So when you come to class, one of the things we'll eventually look at is we're not going to look really too much in our class as to whether a sequence is converging or diverging, but we will be looking a little more carefully at whether a series is converging or diverging. And we'll talk a bit about the difference between a sequence and a series. They're obviously related. It's a very small but important difference between the two of them. So I hope this was helpful for you. When you come to class, make sure that you bring your calculators. We'll do an activity pretty early on. It should be a lot of fun. So I'll see you then.